Look up tonight, wherever you are in the world, and you will see light that began its journey before you were born, before your parents were born, perhaps before your great-grandparents walked this earth. The stars you see are not the stars as they exist in this moment, but as they existed years, decades, centuries ago. Their light traveling across the vast emptiness of space to reach your eyes on this particular night, in this particular moment of your existence. The photons that touch your retina have crossed incomprehensible distances, surviving the cold, dark between worlds, threading through cosmic dust clouds and gravitational fields, somehow avoiding absorption by the countless particles floating in the interstellar medium to deliver their message from the distant past. And yet, when we look up at the night sky, we rarely consider that we are looking backward through time, that the cosmic light show above us is a kind of archaeological record written in luminescence, a history book whose pages are made of starlight itself. There is something impossible about this, something that defies our everyday understanding of the world. How can we see the past? How can light, something we experience as instantaneous, the flick of a switch, the flash of lightning, the sudden appearance of the sun over the horizon, take years to traverse the cosmos? The universe seems to operate by rules that contradict the evidence of our senses, that challenge everything we know about time and space and the nature of existence itself. Tonight, we will follow a single beam of starlight on its journey from a distant star to your eye, and in doing so, we will encounter mysteries that astronomers have puzzled over for generations, questions that lead not to answers, but to deeper questions, to revelations that transform our understanding of where we are, and what we are, and how we came to be standing here on this small planet, looking up at the infinite dark. The temperature is cooling now, as night settles over the landscape. You can feel the subtle shift in the air, the way heat rises from the ground where it was stored during the day, creating gentle currents that lift and swirl around you. The sky above transitions from blue to indigo to black, and one by one the stars begin to appear, first the brightest ones, Venus if it's in the evening sky, then the familiar constellations, Orion with his belt and sword, the Big Dipper pointing toward Polaris, the celestial anchor around which the northern sky appears to rotate through the long night. But focus your attention on a single point of light, not the brightest, not the most famous, but one of the countless anonymous stars scattered across the dome of heaven. A small white dot that seems to flicker and pulse as Earth's atmosphere disturbs its beam. This is where our journey begins. This is the story of how that light came to you, and what it means, and why the journey itself might be the most profound mystery in the universe. Act 1. The official story. According to our current understanding, backed by decades of astronomical observation and mathematical calculation, the light from a typical star visible to the naked eye has traveled somewhere between 4 and 1,000 light-years to reach Earth. The nearest star system, Alpha Centauri, is 4.37 light-years away, meaning the light you see from it tonight left that star in early 2020, during the first months of a global pandemic when the world was transforming in ways no one could have predicted. The mechanism is straightforward, or so it seems. A star is a massive ball of hydrogen gas compressed by its own gravity to such extreme densities and temperatures that hydrogen atoms fuse together to form helium, releasing enormous quantities of energy in the process. This energy works its way outward from the core through the dense stellar material, taking thousands or even millions of years to reach the star's surface, where it is finally released into space as light and heat, streaming outward in all directions at the maximum speed the universe allows. 299,792,458 meters per second, the speed of light, the cosmic speed limit that nothing with mass can ever reach, let alone exceed. This explanation was formalized in the early 20th century by physicists like Arthur Eddington and Hans Bethe, who worked out the nuclear physics of stellar fusion in the 1920s and 1930s. Eddington, in particular, was fascinated by the question of how stars could continue burning for billions of years without exhausting their fuel, and he correctly theorized that hydrogen fusion, converting mass directly into energy according to Einstein's famous equation E equals mc squared, was the answer to this cosmic riddle. The mathematics are elegant, the observations consistent, the theory tested and retested countless times. We can predict with remarkable precision how stars of different masses will evolve over time, how long they will shine, what wavelengths of light they will emit, how they will eventually die, either fading into cold darkness or exploding in spectacular supernova that briefly outshine entire galaxies. The science is settled, they say. We understand how stars work, and therefore we understand the light that comes from them, and therefore we understand what we see when we look up at the night sky. But there is something curious here, something that doesn't quite fit. If the light we see from a distant star left that star decades or centuries ago, and if that star is moving through space, orbiting the galactic center at hundreds of kilometers per second, and if we are also moving through space on our orbiting planet around our orbiting sun, all of us caught in the great cosmic dance of gravity and momentum, then the light we see should be arriving from where the star was, not where it is. Yet when astronomers point their telescopes at stars based on current positions calculated from historical observations, accounting for proper motion and parallax, and all the complex orbital mechanics involved, they find the stars exactly where the calculations predict they should be, as if the light somehow knows where the star is now, not where it was when the photons began their journey. This is the first crack in the official story, a subtle detail that most people never notice, but one that hints at something deeper, something stranger about the nature of light and time and the relationship between observer and observed. Act 2. The First Crack. The man who first truly understood that light travels at a finite speed was Ole Rømer, a Danish astronomer working at the Paris Observatory in the 1670s. He wasn't studying stars, however, but the moons of Jupiter, those 4 bright points of light that Galileo had discovered orbiting the giant planet, proving that not everything in the cosmos revolved around Earth. Rømer was tasked with creating detailed tables predicting when Jupiter's innermost large moon, Io, would disappear behind the planet and when it would re-emerge on the other side. This was important work for navigation, as accurate astronomical tables allowed sailors to determine their longitude at sea, a matter of life and death, in an age when ships regularly vanished without trace into the vastness of the oceans. But Rømer noticed something peculiar. When Earth was moving away from Jupiter in its orbit, the eclipses of Io occurred later than predicted, and when Earth was moving toward Jupiter, the eclipses occurred earlier than predicted. The discrepancy was small but consistent, building up to a total difference of about 22 minutes over the course of Earth's year. In 1676, Römer proposed a radical explanation. Light takes time to travel across space, and when Earth is farther from Jupiter, the light has farther to travel, arriving later than when Earth is closer. From his observations, he calculated that light takes about 22 minutes to cross the diameter of Earth's orbit, which, given the dimensions of the solar system as they were understood at the time, gave him a speed of light fairly close to the modern value, though technology would not exist to measure it precisely for another 2 centuries. This was the discovery that changed everything, that revealed the universe operates not in the instantaneous present, but in layers of different pasts, each object we see showing us not how it is, but how it was, the image delayed by the time it takes light to bridge the distance. Yet here is where the mystery deepens, because Römer himself couldn't explain why light should have a speed at all. What is light made of that would constrain it to a particular velocity? In Römer's time, and for 2 centuries afterward, scientists believed light was either a wave in some invisible medium called the luminiferous ether, or a stream of particles that Newton had called corpuscles. If light was a wave, it needed something to wave in, just as sound needs air and water waves need water. If light was particles, then what were those particles made of? And why did they always travel at exactly the same speed? Never faster, never slower. The ether theory seemed promising. Perhaps all of space was filled with this invisible substance, and light was simply a vibration propagating through it, the same way sound propagates through air. This would explain light's constant speed. It would be determined by the properties of the ether, just as the speed of sound is determined by the properties of air or water or whatever medium it's traveling through. But there was a problem, a profound problem that wouldn't be discovered until 1887, when 2 American physicists named Albert Michelson and Edward Morley conducted what might be the most famous failed experiment in the history of science. Acti 3, the scientific investigation. Michelson and Morley reasoned that if light travels through a medium called ether, and if Earth is moving through space at about 30 kilometers per second as it orbits the Sun, then Earth must be moving through the ether the way a ship moves through water. And just as the speed of water flowing past a ship differs depending on whether the ship is moving with the current or against it, the speed of light measured on Earth should differ depending on whether Earth is moving toward or away from the light source. They designed an exquisitely sensitive instrument called an interferometer, which splits a beam of light into 2 perpendicular paths and then recombines them. If one path is traveling with Earth's motion through the ether and the other is traveling across it, the light beams should take slightly different amounts of time to complete their journeys, arriving back at the recombination point slightly out of phase, creating an interference pattern that could be measured with extraordinary precision. They performed the experiment in 1887 in Cleveland, Ohio, in a laboratory basement to minimize vibrations, floating their apparatus on a pool of mercury to eliminate any possible disturbance from the building itself. They measured the speed of light traveling north-south and east-west, then rotated the apparatus 90 degrees and measured again, then repeated the measurements at different times of day and different times of year, when Earth would be moving in different directions through the hypothetical ether. The result was shocking. They found no difference. None. The speed of light was identical in all directions, at all times, regardless of Earth's motion through space. It was as if the ether didn't exist, or as if Earth was somehow stationary in the ether, which made no sense given that Earth is obviously moving around the Sun, and the Sun is moving around the galactic center, and the galaxy itself is moving through intergalactic space. Everything is moving, all the time, yet light travels at exactly the same speed relative to every observer, regardless of their motion. They repeated the experiment with even greater precision. They checked their equipment, their calculations, their assumptions. Other scientists, skeptical of the result, built their own interferometers and conducted their own measurements. The answer was always the same. The speed of light was constant, invariant, apparently independent of the motion of the source or the observer, a result that violated every intuition about how motion and velocity should work. If you're standing still and someone throws a ball at you at 20 meters per second, and then you start running toward the person throwing the ball at 10 meters per second, the ball appears to be moving toward you at 30 meters per second. The two velocities add together. This is common sense, confirmed by everyday experience and by Newtonian physics, the mathematical framework that had successfully explained motion and gravity for 200 years. But light doesn't work this way. If a star emits light at the speed of light, and Earth moves toward that star at 30 kilometers per second, the light still arrives at Earth, traveling at exactly the speed of light, not the speed of light plus 30 kilometers per second. The velocities don't add. It's as if the universe has different rules for light than for everything else, as if light exists in its own category of phenomena, playing by its own mysterious laws. Scientists tried to save the ether theory. Perhaps Earth drags the ether along with it, they suggested, the way a moving ship drags a thin layer of water along its hull. But other experiments showed this couldn't be the case. Perhaps the ether contracts in the direction of motion, they proposed, or perhaps moving objects shrink in the direction they're moving, perfectly compensating for the expected change in light's speed. These explanations grew increasingly baroque, increasingly desperate, adding layers of complexity to account for observations that seemed to suggest a simpler but more radical conclusion. The truth, when it finally emerged, would require abandoning some of our most fundamental assumptions about the nature of reality itself. Act 4. The Impossibility. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that changed everything. His name was Albert Einstein, and his paper was titled On the Electrodynamics of Moving Bodies, though it would come to be known as the special theory of relativity. Einstein began with two simple postulates. First, that the laws of physics are the same in all inertial reference frames, meaning an observer moving at constant velocity should see the same physical laws operating as a stationary observer. And second, that the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. From these two assumptions, he derived a series of consequences that seem impossible, that violate our intuitive understanding of space and time, yet which have been verified by countless experiments over the past century. Time, he showed, is not absolute. A clock moving relative to an observer runs slower than a clock at rest relative to that observer. This is not an illusion or an error in measurement. Time itself literally passes more slowly for the moving clock, by an amount that can be calculated precisely from the relative velocity. Space is not absolute either. An object moving relative to an observer is contracted in the direction of motion, actually physically shorter than it would be if it were at rest. And simultaneity, the concept that two events either happen at the same time or they don't, is also relative. Two events that appear simultaneous to one observer will occur at different times for another observer moving at a different velocity. The mathematics are unambiguous, and the implications are staggering. If you were to board a spacecraft and accelerate to a significant fraction of the speed of light, traveling out to a distant star and then returning to Earth, you would find that less time has passed for you than for the people who remained behind. They might have aged 50 years, while you aged only 20. This is not science fiction. This is established physics, confirmed by experiments with atomic clocks on airplanes and satellites, which show exactly the predicted time dilation effects, their readings diverging from identical clocks left on Earth's surface by precisely the amounts Einstein's equations predict. But here is the deeper mystery. Why does the universe work this way? Why is the speed of light constant? Why does time slow down and space contract for moving objects? Einstein's equations describe these phenomena with remarkable precision, but they don't explain why the universe has these properties rather than others. Consider the number itself: 299,792,458 meters per second. Why this speed and not some other? Is it arbitrary, a cosmic accident, one of many possible values that could have been set when the universe began? Or is it fundamental, somehow embedded in the deepest structure of reality, a number that couldn't be different without changing the very nature of existence? Modern physics suggests the latter. The speed of light, it turns out, is related to other fundamental constants in nature: the electric constant and the magnetic constant, the properties of empty space that determine how electric and magnetic fields propagate. The speed of light is precisely the speed at which electromagnetic waves, which is what light is, must travel given these properties of space itself. In a sense, the speed of light is the speed of causality, the maximum rate at which information or influence can propagate from one point in space to another. But this just pushes the mystery back a step. Why do the electric and magnetic properties of space have the values they have? Why is the structure of space-time such that it imposes this particular speed limit on the universe? And there's another puzzle, one that few people consider. If light from a distant star was emitted 100 years ago, when that star was in a different position than it is now, why don't we see multiple images of the star, one from each point along its path over the past century? The light emitted when the star was at position A should arrive at a different time than the light emitted when the star was at position B, and so on for every moment of the star's journey through space. We should see a trail, a blur, a streak across the sky showing the star's path over time. Yet we don't. We see a single point of light, crisp and clear, as if all the light that left the star over the years somehow knows to arrive at our telescope at precisely the same moment, perfectly synchronized, despite having been emitted from different locations at different times. The photons that left the star when it was 10 light-years away arrive at the same instant as the photons that left when it was 10.0001 light-years away, and those that left when it was 10.0002 light-years away, all of them converging on our eye, or telescope, with impossible precision, creating a single, stable image of a star that no longer exists in the position we see it. Act 5. The Hidden Design. Look deeper into the nature of light, and stranger patterns emerge. Patterns that suggest the universe operates according to principles we are only beginning to glimpse. Light, we now know, is both wave and particle, existing in a state of quantum superposition until the moment it is observed. A single photon, the smallest possible unit of light, can somehow pass through two slits simultaneously, interfering with itself to create a pattern on a screen that only makes sense if the photon took both paths at once, existing in multiple states until measurement forces it to choose one reality. This is the famous double-slit experiment, first performed with light by Thomas Young in 1801, and repeated countless times since with increasingly sophisticated apparatus. When you send light through two narrow slits and observe the pattern on a screen behind them, you don't see two bright lines corresponding to the two slits. Instead, you see an interference pattern. Multiple bright and dark bands, the signature of waves overlapping and reinforcing or canceling each other out. But here's what makes it impossible to comprehend. If you send photons through the slits one at a time, so slowly that only a single photon is traveling through the apparatus at any given moment, the interference pattern still appears. Each individual photon somehow knows about both slits, interfering with itself, taking what physicists call a superposition of all possible paths through the system simultaneously. Yet if you place a detector at the slits to observe which path each photon takes, the interference pattern vanishes, replaced by two simple bright bands, as if the photon could only go through one slit or the other after all. The act of observation changes the outcome of the experiment, not by disturbing the photon in some crude mechanical way, but by collapsing its wave function, forcing it to resolve from a state of multiple possibilities into a single actuality. This suggests something profound and unsettling about the nature of reality. That the universe at its most fundamental level exists in a state of potentiality rather than fixed actuality. That what we think of as objective reality, independent of observation, may not exist in the way we assume. That the cosmos itself might be, in some sense, incomplete until observed, measured, witnessed by conscious beings who collapse the wave function and crystallize possibility into existence. The mathematics of quantum mechanics, developed in the 1920s by physicists like Heisenberg, Schrödinger, and Dirac, describe these phenomena with incredible precision. The equations work perfectly, predicting experimental outcomes to many decimal places. And yet, nearly a century later, physicists still argue about what the equations mean, what they tell us about the fundamental nature of reality. Some say the wave function represents our knowledge or information about the system, not the system itself. That the photon always takes one path or the other, we just don't know which until we measure it. Others say the wave function is the system, that reality literally exists in multiple states simultaneously until observation forces it to choose. Still others propose that every measurement causes the universe to split into multiple branches, each representing one possible outcome, so that there are countless parallel universes existing alongside our own, each containing a version of you experiencing a different outcome of every quantum event that affects you. And through all of this theoretical debate, light continues streaming through the cosmos, photons emitted billions of years ago, still traveling through space, carrying information about the early universe, about the formation of galaxies and stars, about the chemical composition of distant worlds, about the expansion of space itself. When we look at the most distant galaxies visible to our largest telescopes, galaxies more than 13 billion light-years away, we are seeing light that left those galaxies when the universe was young, less than 1 billion years old. We are literally looking back through time to an era when the first stars were being born, when the cosmos was still hot and dense, when the structures we see today, the cosmic web of galaxies, the vast voids and filaments and clusters, were just beginning to form from the nearly uniform distribution of matter left over from the Big Bang. The cosmic microwave background radiation, discovered accidentally in 1964 by Arno Penzias and Robert Wilson, comes from an even earlier era, just 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space for the first time. This radiation has been traveling for 13.8 billion years, stretched by the expansion of space from high-energy visible light to low-energy microwaves, arriving at our radio telescopes today as a faint whisper from the dawn of time, carrying encoded in its subtle variations the imprint of quantum fluctuations from the first fraction of a second of the universe's existence. In a real sense, we live inside a sphere of light, receiving information from all directions about the history of the cosmos. Each photon a message from the past, the entire observable universe revealed to us only because light has this remarkable property of traveling at a finite but very fast speed, preserving information across vast distances and times. But why should light be able to do this? Why should the universe be constructed in such a way that information is preserved, that we can look back through time, that the past remains accessible to observation even though it no longer exists in the present moment? Act 6. The Mystery Deepens. There is something we haven't discussed yet, something that astronomers take for granted, but which, when you examine it closely, becomes increasingly difficult to explain. Light from distant stars arrives at Earth encoded with information about those stars' composition, temperature, motion, age, and physical properties. When we pass starlight through a prism or diffraction grating, spreading it into a spectrum, we see not a smooth rainbow, but a pattern of bright and dark lines, emission and absorption lines, each corresponding to a specific chemical element in the star's atmosphere. This technique, called spectroscopy, allows us to determine that stars are made primarily of hydrogen and helium, with smaller amounts of heavier elements like carbon, nitrogen, oxygen, iron. We can measure the surface temperature of a star from the overall shape of its spectrum. We can detect planets orbiting distant stars by observing the subtle wobble in the star's motion caused by the planet's gravity, revealed by the Doppler shift in the spectral lines. We can even analyze the atmospheres of those planets by looking at how they absorb starlight passing through them during transits. But here is the mystery. Why should the light emitted by atoms in a distant star be identical to the light emitted by the same type of atoms in a laboratory on Earth? An electron in a hydrogen atom in a star thousands of light years away, undergoing a quantum transition from a higher energy level to a lower one, emits a photon of precisely the same wavelength, 656.3 nanometers for the famous H-alpha line, as an electron making the same transition in a hydrogen atom in a lab. The match is exact to many decimal places, showing no variation with distance or time or location in the universe. This implies that the fundamental properties of matter, the mass and charge of electrons, the mass and charge of protons, the strength of the electromagnetic force that binds them together, are identical everywhere in the universe and have remained constant over billions of years. The universe could have been constructed differently. The fundamental constants could vary from place to place, or change over time, or depend on local conditions. Yet as far as we can tell, they don't. Physicists have looked for evidence of varying constants by comparing the spectra of distant galaxies, whose light left them billions of years ago, with the spectra we observe in labs today. So far, they have found no convincing evidence of change. The fine structure constant, which determines the strength of electromagnetic interactions, appears to have the same value at all times and places. The ratio of the proton mass to the electron mass is the same in galaxies 10 billion light-years away as it is here on Earth. This is simultaneously reassuring and perplexing. Reassuring because it means we can trust our observations of the distant universe. The physical laws that operate there are the same ones that operate here, so our interpretations of what we see are probably correct. Perplexing because there's no obvious reason why the universe should be this way. Why should physical laws be universal rather than local? Why should constants remain constant rather than varying over time? Some physicists have proposed that our universe is just one of many in a vast multiverse, each with different values for the fundamental constants, and we happen to live in one where the constants have values compatible with the emergence of stars, planets, and life. In most universes, the constants might be slightly different, resulting in cosmos that are inhospitable to complexity. Universes where stars never form, or form but burn out too quickly, or where atoms cannot bind into molecules, or where gravity is too weak to pull matter together, or too strong and causes everything to collapse. This is called the anthropic principle. We observe the constants to have life-compatible values because if they didn't, we wouldn't be here to observe them. It's a kind of observational selection effect, a philosophical explanation rather than a physical one. And many scientists find it unsatisfying, feeling that it raises more questions than it answers. And there is another mystery embedded in starlight, one that only revealed itself in the 20th century when astronomers began making systematic measurements of the velocities of distant galaxies. Acti 7. The pattern recognition. In the 1920s, Edwin Hubble, working at the Mount Wilson Observatory with what was then the world's largest telescope, discovered something extraordinary. Nearly all galaxies outside our local group were moving away from us, and the farther away they were, the faster they were receding. He determined this by measuring the redshift of their light, the way spectral lines were shifted toward longer, redder wavelengths compared to the same lines in nearby stars. The redshift could be interpreted as a Doppler shift, the same effect that causes an ambulance siren to sound higher-pitched when approaching and lower-pitched when receding. The greater the redshift, the faster the galaxy was moving away from us. But here was the remarkable pattern. The recession velocity was proportional to distance. A galaxy twice as far away was moving away twice as fast. A galaxy 10 times farther was moving 10 times faster. This relationship, now called Hubble's law, held for every galaxy he could measure, suggesting something profound about the structure of the cosmos. The universe, it seemed, was expanding, not expanding into anything. There is no outside to expand into, but expanding in the sense that the distance between galaxies was increasing over time, as if space itself were stretching, carrying galaxies along with it, like raisins in rising bread dough. If you run the expansion backward in time, you arrive at a moment about 13.8 billion years ago, when all the matter and energy in the universe was compressed into an infinitely dense point, a singularity from which space and time themselves emerged. This is the Big Bang, the origin moment of our cosmos, though the name is misleading. It wasn't an explosion in space, but an explosion of space, a sudden expansion that created the universe as we know it. The light from distant galaxies carries the signature of this expansion. The photons have been traveling for billions of years through space that is itself expanding, and as space stretches, the wavelengths of the photons stretch too, becoming redder and redder the longer they travel. The most distant galaxies we can see have redshifts so large that light originally emitted in the ultraviolet part of the spectrum arrives at Earth as infrared radiation, stretched by more than a factor of 10 by the expansion of space during its billions years journey to our telescopes. This expanding universe was predicted by Einstein's general theory of relativity before it was observed. Though Einstein himself initially rejected the idea, considering it so counterintuitive that he modified his equations by adding a cosmological constant to keep the universe static. When Hubble's observations proved the universe was indeed expanding, Einstein reportedly called this the biggest blunder of his career. Though ironically, modern observations have shown that the cosmological constant, representing what we now call dark energy, is real after all, and is causing the expansion of the universe to accelerate. The pattern extends beyond individual galaxies to the large-scale structure of the universe itself. When astronomers map the positions of millions of galaxies across the sky, a cosmic web emerges. Vast filaments of galaxies stretching across hundreds of millions of light years, connecting dense clusters and surrounding enormous voids nearly empty of visible matter. This structure is the result of gravity-amplifying tiny density variations that existed in the very early universe, variations that we can still detect today in the cosmic microwave background radiation. The universe, it seems, remembers its origins, preserving in its current structure the imprint of quantum fluctuations from the first fraction of a second of its existence, magnified by billions of years of gravitational amplification into the galaxies and clusters we see today. And every photon of starlight streaming through this cosmos carries information about this grand structure, about the journey it took from emission to observation, about the expansion of space and the distribution of matter it traveled through along the way. Act 8. The Cosmic Connection. Pull back further now, expanding your awareness from single stars to entire galaxies, from galaxies to clusters, from clusters to the observable universe as a whole, and a new level of mystery reveals itself. The universe is not just expanding, it's expanding in a very specific way. Measurements of distant supernovae, which serve as standard candles because their intrinsic brightness is known, show that the expansion is accelerating. Galaxies that are already moving away from us are moving away faster and faster over time, as if some mysterious force is pushing them apart, overcoming the attractive pull of gravity that should be slowing the expansion down. This force, whatever it is, has been named dark energy, though the name reveals our ignorance rather than our understanding. We don't know what dark energy is, what causes it, why it has the strength it does, or why it exists at all. We only know that it must exist, because without it, the observations don't make sense. About 68% of the total energy content of the universe is in the form of dark energy, based on measurements of the cosmic microwave background and the large-scale structure of galaxies. Another 27% is dark matter, a different mysterious substance that interacts with normal matter only through gravity. We know dark matter exists because galaxies rotate too fast. The stars in their outer regions move at speeds that would fling them off into space unless there was much more mass present than we can see, providing the gravitational glue to hold everything together. We can map the distribution of dark matter by observing how its gravity bends light from background galaxies, a phenomenon called gravitational lensing. And these maps show vast halos of dark matter surrounding every galaxy, invisible but undeniably present. That leaves only about 5% of the universe in the form of ordinary matter. The protons and neutrons and electrons that make up atoms, stars, planets, and people. We are, quite literally, made of the rare stuff, the minority component of the cosmos, the small fraction of the universe's contents that interacts with light, that can be seen and touched and studied directly. The light from stars, then, is the light from this 5%, the visible portion of a universe that is mostly invisible, dominated by mysterious substances we can only infer from their gravitational effects. Every photon you see in the night sky has traveled through this dark ocean, bent by invisible matter, stretched by mysterious energy, somehow making it across billions of light years of space filled with things we don't understand to reach your eye. And here is where the mystery becomes almost vertiginous in its implications. The photon that reaches your eye tonight, the one you're focusing on as you lie here in the dark, began its journey from a star perhaps hundreds of years ago, when that star was in a completely different position in space, when Earth was in a different position, when you didn't exist, and neither did your parents or grandparents. The photon has traveled through a universe that was slightly smaller then than it is now. Space has expanded during its journey, stretching the photon's wavelength, stealing a tiny amount of its energy, shifting its color slightly toward the red. It has passed through clouds of interstellar gas and dust, some of which absorbed other photons while allowing this one to pass through. It has navigated around the gravitational fields of stars and planets and black holes, its path bent by the curvature of space-time described by Einstein's equations. It has survived, somehow, when countless other photons emitted by the same star at the same moment were absorbed by dust grains, or scattered by electrons, or captured by the atmospheres of planets. This particular photon made it through all obstacles, threaded the cosmic maze, crossed the incomprehensible distance from there to here, from then to now, to deliver its tiny quantum of energy to your retina, triggering a cascade of chemical reactions that translate into an electrical signal traveling along your optic nerve to your brain, where it is somehow, and this is perhaps the deepest mystery of all, transformed into the conscious experience of seeing a point of light in the night sky. What are the odds? What is the probability that this particular photon, out of the countless trillions emitted by stars across the observable universe every second, would complete this specific journey and arrive at this specific eye at this specific moment? The number is so small as to be effectively zero, and yet here you are, seeing it happen, participating in this impossible coincidence, this convergence of photon and observer across cosmic distances and times. Asit 9. The Sacred Space. Now let us enter into the inner nature of the photon itself, into the quantum realm, where all our comfortable intuitions about reality break down completely. A photon is the smallest possible unit of electromagnetic radiation, a quantum of light that cannot be subdivided further. It has no mass, yet it carries energy and momentum. It has no charge, yet it is the carrier of electromagnetic force, the mediator of all electrical and magnetic interactions. It travels at the speed of light because it is light, because it is a ripple in the electromagnetic field, and the speed at which such ripples propagate is determined by the fundamental structure of space-time itself. But here is something strange about the photon's perspective, if we can speak of such a thing. From the photon's frame of reference, if one could adopt it, no time passes at all during its journey. According to the equations of special relativity, as an object approaches the speed of light, time dilation becomes more extreme, and at exactly the speed of light, time dilation becomes infinite. For the photon, the moment of its emission from a distant star and the moment of its absorption in your eye are the same moment, separated by no time whatsoever. The photon experiences its entire journey, whether it lasts nanoseconds or billions of years from our perspective, as a single instant. The beginning and end of its existence are simultaneous in its frame of reference. In a sense that is mathematically precise, though conceptually impossible to visualize, the photon exists outside of time, connecting distant events across the universe in a web of instantaneous relationships that only appears to unfold over time from the perspective of observers like us, observers who are moving slower than light and are therefore subject to the flow of time. This creates a kind of sacred geometry, a network of connections between all points in space-time that have exchanged photons. Every atom in your body that was once part of a star, every calcium atom in your bones and iron atom in your blood was forged in stellar furnaces and scattered into space when those stars exploded as supernovae. And during their time as part of those stars, they emitted and absorbed countless photons, connecting them instantaneously from the photon's perspective to everything else in the universe. You are made of stardust, as the famous phrase goes, but more than that, you are made of atoms that participated in these timeless connections, that were part of this vast network of electromagnetic interactions spanning the cosmos. The light that falls on you now from the sun is connecting you, in the eternal present of the photon's experience, to the nuclear reactions occurring in the solar core. Even though, from your perspective, those reactions happened 8 minutes ago, the time it takes light to travel from sun to earth. Enter deeper into this mystery, into the quantum nature of light, and the strangeness intensifies. According to quantum electrodynamics, the theory developed by Richard Feynman and others in the 1940s and 1950s, a photon traveling from point A to point B doesn't just take the straight path between them. It takes all possible paths simultaneously, every conceivable route through space, every zigzag and detour and loop, even paths that go backward in time and then forward again. The mathematics requires this. To calculate the probability of a photon getting from A to B, you must sum over all possible paths, each contributing a complex number whose phase depends on the action along that path. Most paths cancel out through quantum interference, their phases adding destructively, but a narrow range of paths near the classical straight line add constructively, reinforcing each other to create the illusion that the photon took a single, definite path. But it didn't. It took all paths. It explored every possible route through space-time, and only in the aggregate, when you sum over all possibilities, does the classical behavior emerge, the appearance of a photon traveling in a straight line at the speed of light. This is not metaphor or speculation. This is the mathematical structure of quantum field theory, tested experimentally countless times and found to predict observable phenomena with extraordinary accuracy. The theory has been verified to 1 part in a trillion, making it the most precisely tested physical theory in history. Yet, what it describes is a universe far stranger than the one we experience with our senses. A universe where particles exist in superpositions of states, where events are fundamentally probabilistic rather than deterministic, where the act of observation somehow collapses infinite possibility into singular actuality, where photons simultaneously take all paths and no single path, existing in a quantum haze that resolves into classical certainty only when we perform measurements. The photon entering your eye right now exists in this liminal state, neither particle nor wave, until the moment of interaction with the rhodopsin molecules in your retinal cells forces it to manifest as one or the other, to deposit its energy in a specific location, to trigger the specific chemical cascade that will be interpreted by your brain as a point of light in the darkness. Act 10. The Hidden Depths. Modern astronomy has revealed layers of complexity in starlight that earlier generations never suspected, mysteries nested within mysteries, each discovery opening new questions rather than closing old ones. Consider the cosmic microwave background, that faint radiation coming from all directions in space, the afterglow of the Big Bang. When Penzias and Wilson first detected it in 1964, it seemed perfectly uniform, the same temperature, about 2.7 Kelvin above absolute zero, no matter where they pointed their antenna. This uniformity was itself mysterious, requiring explanation. But the deeper mystery only emerged later, when more sensitive instruments revealed tiny variations in the temperature, fluctuations of 1 part in 100,000. These fluctuations are the seeds of all cosmic structure, tiny quantum variations in density from the very early universe, stretched to cosmic scales by inflation, a hypothetical period of exponential expansion in the first fraction of a second after the Big Bang. Gravity amplified these small variations over billions of years, pulling matter together into ever denser clumps, forming the first stars, then galaxies, then clusters of galaxies, building up the cosmic web we see today. But here is what makes this impossible to fully comprehend. Those quantum fluctuations originated as uncertainty in the positions and velocities of particles at the Planck scale, the smallest possible scale where quantum mechanics and gravity both matter, where space-time itself becomes foamy and uncertain, where distances smaller than 10 to the minus 35 meters and time shorter than 10 to the minus 43 seconds lose meaning. Somehow, random quantum jitter at the smallest possible scale was inflated to the largest possible scale, spanning the entire observable universe, creating variations in the density of matter that eventually gave rise to stars and planets. And on at least one planet, to life and consciousness and you, lying here now, contemplating the origins of the light you see. The chain of causation stretches from quantum uncertainty at the beginning of time to your subjective experience in this moment, connected by 14 billion years of cosmic evolution, by the physics of gravity and nuclear fusion, by chemistry and biology, by the particular arrangement of atoms in your brain that somehow gives rise to the feeling of what it is like to be you, experiencing this moment, this thought, this sensation of light entering your awareness. And every step of this chain is mediated by light, by photons carrying information and energy across the cosmos, connecting cause to effect, past to present, the quantum realm to the classical realm, the physical to the experiential. Recent observations have added new puzzles to this already mysterious picture. The James Webb Space Telescope, launched in 2021, has been observing the earliest galaxies, those formed just a few 100 million years after the Big Bang, and finding them surprisingly mature, surprisingly well organized, with structures that shouldn't have had time to form, according to our current models of galaxy evolution. Some of these early galaxies are too massive, containing too many stars for their age. Others show evidence of heavy elements, carbon, oxygen, iron, that should only be present after multiple generations of stars have lived and died, enriching the interstellar medium with the products of nuclear fusion and supernova explosions. Yet these galaxies existed when the universe was young, when there hadn't been time for multiple stellar generations. The light from these galaxies, stretched by cosmic expansion from visible wavelengths to infrared, tells us something is incomplete in our understanding. That the early universe was perhaps more complex, more active, more efficient at forming structures than we thought. The standard model of cosmology, which has been so successful at explaining most observations, may need modification to account for what we're now seeing in the deepest images of the cosmos. Layer upon layer, the universe reveals complexity. Galaxies contain supermassive black holes at their centers, millions or billions of times more massive than the Sun, and these black holes seem to influence the formation and evolution of their host galaxies in ways we're still working to understand. The light from matter falling into these black holes, heated to millions of degrees by friction and compression, can outshine all the stars in the galaxy combined, creating quasars visible across billions of light years. Some galaxies collide and merge, their shapes distorted by gravitational interactions, triggering bursts of star formation as gas clouds are compressed. We can watch these collisions unfold, not in real time, which would require millions of years, but by observing many different galaxies at different stages of merger, assembling a composite picture of the process from still frames distributed across cosmic time and space. And threading through all of this, connecting observer to observed, past to present, distant to near, is light. Photons streaming through the universe, each one carrying its tiny payload of information, each one a messenger from somewhere and someone else, arriving here, now, in your awareness. Act 11. The Cataclysm. The stars we see tonight are not the stars that will shine on distant future generations, just as they are not the stars that shone on ancient civilizations. The sky is constantly changing, though the changes are imperceptible on human timescales, visible only when we compare observations separated by decades or centuries. Stars are born in clouds of gas and dust, collapsing under their own gravity until their cores become hot, and dense enough for nuclear fusion to begin. They spend most of their lives steadily burning hydrogen into helium in a state of equilibrium between the inward pull of gravity and the outward pressure of the energy generated by fusion. But this equilibrium cannot last forever. When a star exhausts the hydrogen in its core, it begins to change, expanding and cooling on the outside while its core contracts and heats up, eventually becoming hot enough to fuse helium into carbon and oxygen. Low-mass stars like our Sun will eventually shed their outer layers as planetary nebulae, beautiful shells of glowing gas expanding into space, leaving behind a white dwarf, a stellar corpse the size of Earth, but with the mass of the Sun, slowly cooling over trillions of years until it becomes a black dwarf, a cold, dark cinder drifting through space. High-mass stars meet more dramatic ends. When they exhaust all possible fusion reactions, their cores collapse catastrophically in a fraction of a second, and the resulting shockwave blows the rest of the star apart in a supernova explosion that briefly outshines an entire galaxy. These explosions scatter heavy elements into space. All the carbon and oxygen and nitrogen and iron and gold and uranium in the universe were created in stellar cores or in supernova explosions, meaning that every atom in your body heavier than hydrogen was forged in a star and distributed through space by stellar death. You are, quite literally, the universe contemplating itself, star stuff arranged in such a way as to be capable of thought and feeling and wonder, looking back out at the cosmos from which you came and to which you will return. The cycle continues. The gas and dust ejected by dying stars mix with the interstellar medium, enriching it with heavy elements, providing the raw material for new generations of stars and planets. Our Sun is probably a third-generation star, formed from material that cycled through previous stellar generations, inheriting a rich mixture of elements that made rocky planets possible, that made chemistry complex enough for life to emerge. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin its transformation into a red giant, swelling to perhaps 100 times its current diameter, engulfing Mercury and Venus and possibly Earth. The increased solar radiation will have made Earth uninhabitable long before then. In perhaps 1 billion years, the oceans will boil away, and life as we know it will become impossible. This is the cataclysm built into the structure of stellar evolution, the inevitable price of being a planet orbiting a star. But zoom out further, and the cataclysms multiply. Galaxies collide, their stars mostly passing by each other harmlessly. Space is so vast that even when galaxies merge, direct stellar collisions are rare. But the gravitational interactions can fling stars out of their galaxies entirely, sending them wandering through intergalactic space. The Milky Way and the Andromeda Galaxy are currently approaching each other and will collide in about 4 billion years, merging over hundreds of millions of years into a single larger elliptical galaxy that astronomers have nicknamed Milkomeda. On even larger scales, the accelerating expansion driven by dark energy is pulling galaxy clusters apart, carrying distant galaxies away from us faster and faster. Eventually, billions of years from now, galaxies outside our local group will recede beyond the cosmic horizon, their light stretched to such long wavelengths by the expansion of space that they become undetectable. Future astronomers in Milkomeda, looking out at the universe from a vantage point trillions of years from now, will see a cosmos that appears empty except for their own galaxy, with no evidence of the billions of other galaxies that exist but have been carried beyond the observable horizon by cosmic expansion. They will look up at the night sky and see nothing but darkness beyond their own stars. No cosmic microwave background, no distant galaxies, no evidence of the Big Bang. They will have lost access to the history of the universe, to the story of cosmic origins, unless somehow the knowledge is preserved and passed down through the unimaginable spans of time, separating their era from ours. This is the ultimate cataclysm, not a violent event, but a gradual isolation. The universe growing colder and darker and emptier as expansion carries everything beyond reach, as stars exhaust their fuel and die, as galaxies fade, as the last black holes evaporate through Hawking radiation, until finally, in the inconceivably distant future, the universe reaches a state of maximum entropy, a cold, dark, dilute void where nothing can happen because there are no energy gradients left to drive any process. Yet even this far future remains uncertain. Our understanding of physics is incomplete. Dark energy could change its properties, causing the expansion to slow or even reverse. New physics might emerge at energy scales we haven't yet probed. The universe might be cyclic, undergoing endless phases of expansion and contraction, each Big Bang followed eventually by a big crunch that becomes the next Big Bang, an eternal cycle of death and rebirth. Or our universe might be one bubble in an eternally inflating multiverse, new universes constantly spawning from quantum fluctuations in the inflationary field, each with its own physical laws and constants, an infinite proliferation of realities beyond our capacity to observe or verify. The light that reaches us tonight tells us about the universe as it is and was, but it cannot tell us about all the possibilities that might lie beyond our observational reach, beyond our cosmic horizon, beyond the limits of what light can reveal. Closing, the eternal watch. The sky is beginning to pale now in the east, the first hint of dawn washing out the fainter stars even as the brightest ones remain visible. Venus blazing above the horizon, if it happens to be in the morning sky, the constellations starting their daily disappearance as the sun's light overwhelms them. The photon whose journey we have been following all night has long since been absorbed, its energy transformed, dissipated, redistributed, becoming heat, becoming chemical potential, becoming electrical signals in your neurons, becoming the conscious experience of seeing, remembering, imagining, wondering. It has ended its journey, and yet in ending it has become part of you, has contributed its infinitesimal portion to your moment-by-moment existence, connecting you to the distant star from which it came, making you a participant in the cosmic dance of light and matter and energy. Every moment, day and night, photons are arriving at Earth from across the universe, each one carrying information, each one connecting us to distant places and times, each one a thread in the vast tapestry of light that makes the cosmos knowable, observable, comprehensible, at least in part. We stand on this small planet, orbiting an ordinary star in an ordinary galaxy among billions of galaxies. At this particular moment in cosmic history, when the universe has cooled enough for stars and planets and life to exist, when the expansion is carrying distant galaxies away, but hasn't yet isolated us completely, when we can look up and see the grand sweep of cosmic structure and evolution displayed in the night sky. This moment is precious because it is temporary. The universe of the far future will be a lonelier place. Darker, colder, with fewer stars, and no galaxies visible beyond the local group. The universe of the distant past was too hot and dense for life, too chaotic for stable structures to form. We exist in a narrow window of cosmic time when observation is possible, when consciousness can emerge, when the universe can contemplate itself through beings like us. And what is consciousness but another mystery wrapped inside the mystery of light and matter? How does the electrical activity in your brain, the firing of neurons, the release of neurotransmitters, the opening and closing of ion channels, somehow give rise to the subjective experience of seeing a star, feeling wonder, asking questions about existence? This is the hard problem of consciousness, perhaps the deepest mystery of all, the question of how and why physical processes in the brain generate the inner light of awareness, the felt quality of experience, the sense of being someone, being you, existing now in this moment. The photon from the distant star travels billions of years across the cosmos, navigating the vastness of space, threading through the gravitational maze, arriving finally at your retina, where it triggers a cascade of molecular events. Rhodopsin molecules change shape, ion channels open, electrical signals propagate along nerve fibers to the visual cortex, patterns of neural activation spread through vast networks in your brain, and somehow, miraculously, impossibly, this chain of purely physical events becomes the conscious experience of seeing a point of light in the darkness, becomes the feeling of wonder, becomes the thought about stars and time and existence. Matter arranged in a certain configuration becomes aware. The universe, through you, perceives itself. Starlight scattered across billions of years of space and time converges on conscious observers who can recognize it for what it is, can trace it back to its sources, can understand the physical processes that created it, can ask why it exists and what it means, and whether any of this matters in the vast, indifferent cosmos. Perhaps the meaning is in the asking. Perhaps consciousness is the universe's way of creating meaning, where none exists objectively, of generating purpose and value and beauty through the subjective experience of beings who care about such things. Perhaps we are the universe's way of knowing itself, of transforming blind physical processes into understanding and appreciation and wonder. Or perhaps these are just thoughts arising in brains shaped by evolution to find patterns and assign significance, and the universe itself is indifferent to our interpretations, to our efforts to understand, to our brief flicker of awareness in the cosmic night. The mystery remains unresolved, as it must. We can trace the path of the photon from emission to absorption, can describe its properties mathematically, can predict its behavior with extraordinary precision, can embed it in a vast theoretical framework connecting quantum mechanics to relativity, to thermodynamics to cosmology, can see how it fits into the grand story of cosmic evolution from Big Bang to present day. But the deeper questions: why does the universe exist at all? Why does it have the laws and constants it does? Why is there something rather than nothing? What is the relationship between the physical and the experiential, between matter and mind? These questions remain as mysterious as ever, perhaps permanently beyond our capacity to answer, perhaps even meaningless in some fundamental way we cannot recognize from our limited perspective. And so we watch. We observe, we measure, and calculate and theorize and wonder. We point our telescopes at the sky and collect photons, ancient light from the edges of the observable universe, information about events that occurred billions of years ago, evidence about the history and structure and fate of the cosmos. We build elaborate instruments to detect the faintest signals, to resolve the finest details, to push our observations to the very limits of what physics allows. We do this because we are curious, because we are moved by the beauty and mystery of the night sky, because understanding feels meaningful even if we cannot explain why it should matter. We are pattern-seeking, meaning-making beings, evolved to find order in chaos, to construct narratives that make sense of our experience, to ask questions even when we suspect the questions might have no answers. The stars continue their ancient dance, indifferent to whether anyone observes them, yet somehow we are here, watching, wondering, participating in the grand unfolding of cosmic history, not as passive observers, but as active participants. Our consciousness itself, a cosmic phenomenon, emergent from the same laws and processes that created stars and galaxies and photons streaming through the void. Night fades. Day arrives. The stars disappear from view, but not from existence. They continue shining, continue sending their light streaming across the cosmos, and tonight, when the sun sets again and darkness returns, they will be there still, waiting to be seen, waiting to connect you across space and time to the distant reaches of creation, waiting to inspire wonder and curiosity and questions about existence. This is the eternal watch, the endless vigil of starlight falling on whatever eyes are present to receive it, consciousness emerging again and again wherever conditions allow. The universe repeatedly waking up to see itself, to ask questions about itself, to marvel at its own existence, creating islands of awareness in the vast ocean of unconscious matter and energy. You are one such island, one momentary configuration of atoms arranged in a pattern complex enough to generate awareness, to perceive light, to wonder about your place in the cosmos. You exist now, in this fleeting moment between past and future, between birth and death, between the Big Bang and the ultimate fate of the universe, whatever that might be. The photon's journey is complete. Your journey continues, for now, for a little while, for whatever time remains. The universe expands, stars burn, light travels, consciousness flickers into existence and out again, across the cosmos, across the eons, the universe's way of experiencing itself, of transforming physical processes into felt experience, of creating meaning and beauty and wonder from the blind churning of matter and energy, according to mathematical laws. Rest now. Let your thoughts drift. Let the questions dissolve into the peaceful darkness behind your closed eyes. The stars will be there tomorrow night, and the night after, shining their ancient light across the void, waiting patiently for eyes to see them, for minds to wonder at them, for consciousness to briefly illuminate the cosmic dark. The photons will find you again. They always do, crossing space and time, threading the maze of existence, connecting everything to everything else in the vast web of light that makes the universe knowable, beautiful, mysterious, and somehow, against all odds, worth contemplating. Sleep now. Dream of starlight. Let the cosmic mystery enfold you in its gentle uncertainty, its patient unknowing, its infinite invitation to wonder. The universe will still be here when you wake, still expanding, still evolving, still shining its light into the darkness, still offering its mysteries to anyone willing to look up and ask why. The eternal watch continues. You are part of it. You always were. You always will be. In some sense, your atoms scattered eventually back into the cosmic dance, recycled through future stars and planets, participating still in the great pattern of matter and energy and light that constitutes existence. For now, though, rest. The cosmos can wait. The questions can wait. The mystery will still be there in the morning, unchanged, eternal, perfect in its incompleteness. The last stars fade as dawn breaks. Day arrives. The cycle continues. And somewhere, light is still traveling, photons crossing the cosmic void, carrying their messages from past to future, from distant to near, from unknown to known, bridging the impossible distances, connecting everything, illuminating the dark. This is what light does. This is what you do. Shine briefly in the cosmic dark, connecting past to present, matter to mind, the physical to the experiential, creating meaning where none need exist. Finding beauty in the equations, feeling wonder at the vastness, being, for this moment, the universe's way of knowing itself. Rest now, traveler. Your journey through stardust continues tomorrow. The end is the beginning. The beginning is the end. Light travels. Time flows. Consciousness emerges and dissolves. The mystery remains, perfect and complete in its eternal incompleteness. Sleep